In objective 4, we're going to put together our first and second derivative tests to sketch curves. We're going to do a little review about points of inflection and talk a little bit more about curves. So we're going to start with a nice concave up, concave down, concave up. Okay. So we're going to have some points here. Each section of the curve, something different is happening here. So in our first section on the left, this curve is clearly increasing at an increasing rate. Notice if I drew slopes of tangent lines here, the slopes would become more and more positive. So we say increasing at an increasing rate. Okay, since the curve is increasing, our first derivative would be positive. And since those slopes become more positive, our second derivative is also positive. In the second region, the curve is still increasing, but this time the slopes of those tangent lines become less and less positive, approaching a slope of 0. So this curve is still increasing, but at a decreasing rate. Again, we have that the curve is increasing, so our first derivative would be positive. But our second derivative is now negative. You'll notice here the curve is concave down. So the second derivative again, negative. In the third section of the curve, it's now decreasing, but at an increasing rate. Notice our tangent line slopes would start at 0, okay, and change from there to a more and more negative number. So decreasing at an increasing rate. So our first derivative, negative, slopes of tangent lines are negative here. And our second derivative, the function's concave down, so the second derivative is also negative. So in the fourth region, we still have that the curve is decreasing. This time at a decreasing rate. My first derivative is still negative since the slopes of the tangent lines would still be negative here. And the function has gone back to being concave up, as if this is part of an upward facing parabola. So our second derivative here, positive. We're going to go ahead and move on to the curve sketching portion, putting together our first and second derivative tests. So for our one example today, so for the function given below, we are going to do several things. Find all the critical numbers, then intervals where f is increasing, decreasing, or constant. The intervals where f is concave up or down, or possibly has no concavity. And we want to find all relative maximums, minimums, and points of inflection. we're going to take all of this information and sketch a curve. So the function we're going to be working with here x to the fourth minus 4x cubed. One thing we're going to start with is stuff we learned about polynomials last year. So a polynomial curve with a positive leading coefficient and an even highest power should go high to high. So we know how the end behavior should look. Okay. We're going to start with some things like some x-intercepts. If I can, that'll help me sketch a little bit better. So some x-intercepts here, if I factor out x cubed, I'm left with x minus 4. So I have x-intercepts of 0, multiplicity 3, and 4. You'll remember an odd multiplicity means our function should cross the x-axis. An even multiplicity would bounce. So here they're both odd multiplicity, so it should cross the x-axis at 0 and 4. All right, so the next things we're going to do, critical numbers, increasing, decreasing, and for max and min, that would all be about our first derivative test. So here's our first derivative, 4x cubed minus 12x squared. We want to set this equal to 0, so we're going to factor it. 4x squared, we're left with x minus 3. So I have critical numbers 0 and 3, plus anywhere the function is not differentiable or where the function doesn't exist, but polynomials, they exist everywhere. These are our only critical numbers. So something's possibly happening here, like a max or a min. Okay. And so we're going to do our first derivative test and see what's going on. So 0 and 3 are both zeros of our first derivative, so I'm labeling this number line f prime. We're going to plug in some numbers in between to test. So plugging these numbers back into my first derivative, if we plug in -1, we're going to end up with a positive times a negative, which is a negative. Plugging in 1, we're going to end up with a positive times a negative, which is also negative. And plugging in 4, 2 positives, which will give us a positive. So this tells me where f is decreasing, still decreasing, then increasing. So f is increasing from 3 to infinity, and f is decreasing from negative infinity to 0 and 0 to 3. Something's happening at 0, but there was no sign change, which means it's not a relative minimum or a relative maximum. At 3, though, I did have a sign change. Notice f prime changes from negative to positive, which means f changes from decreasing to increasing. So there should be a relative minimum when x is 3. Now, since we're coming up with the sketch of the function, we should find out where exactly this point occurs. So let's go ahead and plug this back into the original function f. So 3 to the 4th power minus 4 times 3 cubed so negative 27 would be the coordinate pair there. So increasing, decreasing, a relative minimum, never constant, no relative maximums. Something is happening at 0, but it wasn't a min or a max. So let's move on to our second derivative test. Right. So taking from our first derivative, our second is 12x squared minus 24x. And we're going to do the same thing. We set this equal to 0 and factor. So I get my test values here, 0 and 2. You'll see 0 occurred a second time. So most likely, if it's not a relative max or min, it might be that it's a point of inflection. And that's why we were getting that it was a critical number. So something's happening there. It just wasn't one of these things. It might be a point of inflection. So let's go ahead and test these values. The second derivative number line test. So 0 and 2 are both zeros of the second derivative. We'll pick some numbers here to plug in. Plug those back into your second derivative. So plugging in -1, we get a negative times a negative is a positive. Plugging in 1, we get a positive times a negative. And plugging in 3, 2 positives. So remember, our second derivative test tells us about the concavity of f. So this is where f is concave up, down, and up. So we'll write those out. Concave up, negative infinity to 0. And again, 2 to infinity. And concave down, 0 to 2. Okay. We're also looking for any points of inflection. And points of inflection, of course, occur when there's a sign change to the second derivative. So positive to negative, point of inflection at 0. Negative to positive, point of inflection at 2. So point of inflection. And again, because I want my real sketch, I'm going to go ahead and identify the coordinate pairs for these points. So I know at 0, that was one of my x-intercepts. So 0, 0. And if we plug in 2 to our function, we'll end up with negative 16. All right. So increasing, decreasing, constant, all the critical numbers have been found. Right here, 0 and 3. Concave up, down, max, min, point of inflection. Now we're on to the sketch of the graph. You might not always know your x-intercepts for a graph, but if you do, like we do here, it's just more information to help us sketch a more accurate picture. So 0 and 4 are the x-intercepts. We have a few other points here we can plot. So we have 3, -27 for a relative minimum. So I'm not going to draw this to scale here. We'll go ahead and say -27 here. That's our minimum, our relative minimum, so a lowest point for the graph. And then we have 2 points of inflection, one at 0, 0, which we already have, the other at 2, -16, so it's going to be about here. That's a point of inflection. The concavity changes at both of these points. So we need to connect our dots. Remember, the graph is high to high, so we're going to start high, cross at 0, connect these points, and then cross back through 4. But it's a polynomial, so it should be nice and smooth. We also need to make sure that we show the concavity changing here. So the first thing you might do is use your pencil and lightly make a curve. You want to decrease, 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 and then increase. That's what our graph says it does. Okay, it's decreasing negative infinity to 0. It keeps decreasing 0 to 3, and then it increases 3 to infinity. Then we're going to go back and put in our concavity up from negative infinity to 0. So this should appear like an upward facing parabola as it decreases. Okay. Then we have 0 to 2 should change to concave down. So to connect these 2 points, it needs to be like a parabola facing down. Okay. Then we go back to concave up from 2 to infinity. So the rest should be like an upward facing parabola. So again, we have concave up like this. And hopefully you start to see a really pretty curve coming out of this. Let me get rid of all these extra lines. Should be a nice smooth function because it is a polynomial. And I'm just going to go back over it here. A little nice. There we go. There's my nice, smooth, continuous polynomial function. I can see max mins. I can see, which we only have a minimum. I can see my zeros. I can see points of inflection where the concavity changes. Nothing awkward looking in it. So take your time. Use a pencil first. If you want, you can go back over it in pen. Make it look real nice.